continue. All right. Um, uh, Thank you very much for inviting me, Katya, and thank you very much to all the people who've taken the time to come and listen to my talk. I see some very famous people here, so hopefully what I have to say may be of some interest to them. Um, so uh, just to say quickly, so my work is supported by the NSF, and part of this work was done when I was in the University of Helsinki in 2018, and Marty Lasses was kind enough to provide funds for that stay. Oh, okay. Yeah, let's see. Okay, so I'm going to talk about two results that we have. So one is uniqueness for a fixed angle scattering problem. Actually, what we need is data from two directions, not one. So it's the fixed angle scattering problem is still unsolved, but we've come close. Um, so for the fixed angle scattering problem, the operator will be the wave operator, constant speed, and then there'll be a potential Q of X, and we'll be trying to recover the Q of X. And the way we do it is the fixed angle scattering data is actually in the frequency domain. I know mostly things in time domain, so the problem is transformed to a time domain problem with boundary data, and we prove stability for that. It's a formally determined problem, and this work was done with Mikko Salo. And there were two papers. One is already appeared, and one is on the archive. I'll also talk about another result, which is actually very recent, done in the last few months, uh, in which we'll work on recovering coefficients which depend on space and time variables. It's a kind of a fixed angle scattering problem. Again, there'll be plane waves coming only from one direction. So the operator is the wave operator plus Q of xt, and it'll be data coming from that. It's a time domain result. I don't know. I think there is a theory of the frequency domain scattering data, but I don't know that very well. So it's a time domain result. It's also a formally determined problem, and it's based on work we've done with Venki Krishnan and Soman Senapati. And I posted it today, so hopefully it'll be available tonight. I do want to say that actually the references and the literature review in that article, which is the QXT article, it's not complete. We just have the statement of the results and the proofs there. But I will add the literature survey later. So, okay, let me just move my thing here from. Okay, so let me firstly, I want to talk about the fixed angle scattering problem. And actually, there are two long-standing open problems. One is the fixed angle scattering problem, and the other one is the backscattering. And I want to state both of them so that hopefully, So the fixed angle scattering problem is that, so you have this Q of X, which is a compactly supported smooth real valued function. Support is in, say, some ball like this. And we send in a plane wave coming from a direction omega. This omega direction is fixed. And then you measure the far field data in all directions and for all frequencies. So omega is fixed. The far field data is known for all directions theta and all frequencies. And the fixed angle scattering problem is, so omega is fixed, incoming wave is fixed, and the goal is to invert this map from the coefficient to the far field data in all directions and all frequencies. Okay, so the incoming direction is fixed. So that's been a long-standing open problem. And there is another long-standing open problem. I'm sorry, this bar for the Zoom interferes. I can't see it at times. Yeah, okay. So the backscattering problem is, again, same. So you have the coefficient, And in this case, what you do is we send in a plane wave in the direction omega, but we don't measure it all around. We measure the backscattering, which is we measure the response back in the direction minus omega. And we do it for all frequencies. So we do it for every direction, but only backscattering data. And we measure it for all frequencies. And the goal is to invert this. Uh, this problem is unsolved. There are lots of partial results, a lot of important work done by people uh, for the backscattering problem, but it's much harder than the fixed angle scattering problem. In fact, the situation is, I would say, so bad that one doesn't even know that for the backscattering problem, if the backscattering is zero, then the potential is zero. One can't even prove that. Um, so whereas for the fixed angle scattering problem, there's much more progress. And the reason one can partly explain like this is for the fixed angle scattering problem, you're really working with only one solution. You have an incoming wave and you solve it, and you have data for that one solution or in all directions and all frequencies. Whereas for the backscattering problem, there are many solutions involved, one for each direction omega. And for each solution, there's only a little bit of information, just the backscattering direction. So to study backscattering problems, one has to study many solutions of this PDE, but only having a little bit of information for each solution. So putting all things together, that makes it pretty difficult. Whereas fixed angle scattering problem, it's really just only one solution and you work with that. So I will just focus on the fixed angle scattering problem and the backscattering problem. Um, if you're interested, Gunther and I wrote a paper several years ago, and we did a survey, and we have some results, partial results there. So I'll just talk of the fixed angle scattering problem. Oops, sorry. Okay, so B will denote the unit ball. Q will be a real smooth function, which will support it in the ball. And I'm just reiterating the fixed angle scattering problem. It maps the potentials to the fixed angle scattering data. Omega is fixed. Measure the far field in all theta for all frequencies. And so let me give a little bit about what the results are known. And please excuse me if I omit someone or I miss someone. It's not intentional. Please do write to me and I'll make sure I mention it in my articles. Okay, so please do let me know if I omit someone or I make a mistake. So Prosser in 1992 proved the construction of an inverse when the Q is small, and is by constructing a series, and so created the inverse for that. Baylis, Lee, and Moravec in 89 proved that if the fixed angle scattering data is zero, then the potential is zero. So this is the thing I said, which is not even known for the backscattering problem. So if you like, this is like a unique continuation result here. Then Stefanov in 92 proved the injectivity for small q, and Bartzillo et al. In 2018 recently proved that result for much less regular q. And Stefanov in 92 also proved the injectivity of the map F on dense open sets. Okay, and in 93, Greenleaf and Ullman proved that one can recover the principal singularities of Q if Q is a co-normal potential. And Ruiz in 2001 generalized the result to much more, where they allowed Q to be essentially in some HS, and proved in a certain sense that one can recover the principal singularities of Q from the fixed angle scattering data. So that is roughly what was known before. So I will now talk about our result with Mikko Salo on the fixed angle scattering problem. So I'm reiterating the problem. It's the map from the coefficients to the fixed angle scattering data. And what we proved in 2019, that's about a year ago, was the So we can't still prove injectivity of the map F. But what we say is that if you give us fixed angle scattering data from two directions, not one, but two, and they have to be opposite. So you fix a direction omega and you give us fixed angle scattering data from the direction minus omega and from the direction omega. Okay, then we can prove the injectivity of this map. Um, but we can't do it for a single direction yet. Okay, if you give us information only from a single direction, uh, as I said, we cannot prove injectivity, but we have partial results. So it says that suppose you give us information only from a fixed direction one and not the second direction. And if you have FQ equal to the Q and Q plus P have the same data, then we can show P is zero under two constraints. So if P is even or odd in the direction omega, so if you think of omega as say direction parallel to the z-axis, then if the perturbation is even or odd with respect to the z-axis, then of course, if it's even or odd, then if you have one, you have the second direction automatically. So it really goes back to that. But we also have another case. If say if you have it information only in the direction z, and P is controlled in all directions perpendicular to z. So the derivatives of P are controlled in a certain sense. Then also we can prove injectivity from a single direction. Okay, this result actually recently has been extended. So using these techniques, Ma and Miko, very recently, like last 2 months ago, were able to extend similar kinds of results, like the two results that I mentioned here, when they've replaced the wave operator by something with a metric here, Riemannian metric. But the metric has to be certain restricted families because one needs to have a progressing wave expansion and also have Carl-Lewin estimates for it. So those two things constrain a little bit what the metric can be. And again, very recently, in fact, just less than a month ago, Mirono, Machado, and Salo extended these two results to the case where they allow first order perturbation, first order coefficients. So I think it's called the magnetic potential, I believe. And then there is gauge invariance a little bit here. So one can show that you can recover the curl of A and Q. That's what they showed. Okay, so I'm going to talk about just our result here in the first part. I will not talk about I'm sure they will talk about their results some elsewhere. Okay, so what's the idea? How do we prove the injectivity with data from two directions? So again, it's the restatement of the problem. So you send in a plane wave, measure in all directions theta for all frequencies. So if you just formally take the Fourier transform, you can see that, so I haven't yet defined what the far field is, and I'm not going to because, as I said, I'll be working the time domain, I'll just state some things. So if you formally take the Fourier transform, you can see it's going to be solving the time domain equation. And the problem is really this. So let uxt be the solution of the initial value problem in the time domain. And this is the incoming plane wave. Okay. And at least formally, if you take the Fourier transform, that's where you get the solution here. And then you go to the far field from that. Okay. So there is some very special structure of this problem here, which I want to, and that's going to be important for us. And that's what I want to point out. So you send in a plane wave. Of course, there is a response from the medium. And the principal response is just the same delta because this is a zeroth order perturbation. And then there is a lower order thing. So the u of xt is the initial incoming wave plus something which is actually slightly smoother. It's got a Heaviside singularity. And then there is this coefficient u of xt omega. So this is really where our data will be, the u xt omega. Excuse me. Okay. Sorry. Okay. Um, the so the part U here is really where our data is, and I want to just spend a few minutes on the U. So U is a solution of what is called the characteristic initial value problem. Um, so U is, and the solution U is actually just above the half plane here, the inclined plane. It just resides there. And this is very important. The second part, the value of U on this inclined plane is related to the coefficients explicitly. The value at any point x comma t on this inclined plane actually is the integral of Q on a line starting at that point x comma t. Okay, this is very important. Um, so U is directly related to the unknown coefficient Q on this inclined plane. Of course, we don't have data on the inclined plane, but this connection we are going to use in a very important way. Oops, sorry. Okay. So the way we convert, so we have this fixed angle scattering data, which is, for all directions theta, the far field, and k and omega. And we can show it's equivalent to knowing the value of this perturbation u on the boundary of this cylinder. Okay. This is not automatic. It's not just by taking the Fourier transform because, there's questions about decay and stuff. So this has to be done carefully, and it was done rigorously. So we show that the fixed angle scattering data, knowing that is equivalent to knowing the value of this u, this perturbation u, on the boundary of this cylinder. Okay, and right. Okay, so I just want to address this question of the equivalence of the time domain and frequency domain data. So here, the far field data omega was fixed, and we knew information for all theta and all k. And if you people work in the frequency domain, they know that if you know the far field data in all directions for all frequencies, then from that you can extrapolate to the near field data. And then loosely, formally speaking, so if you take the Fourier transform, you get near field data here outside the support. So that's the formal argument, but that has to be made rigorous. Okay, and to show why that, there are still some issues. So suppose you fix your direction omega, and also you fix your direction theta in which you measure. Okay, and then you ask, is there a time equivalent version of that? And there are several candidates, but actually, as far as I know, there is no rigorous proof that there is equivalence between knowing that fixed omega theta data for all k and knowing the corresponding thing in the time domain. Okay, that's as far as I know, it's unknown. And the reason that is important is because if one wants to apply time domain techniques, then I'll just go back for a second, do something. To the backscattering data problem, then it becomes an issue here. Because here we know this, for given omega, we know it only on minus omega, not for all theta. So if you want to convert this into a time domain problem, it's going to be an issue, which first has to be resolved. That if you have omega and theta fixed, then is there a corresponding time domain thing? Okay, and that has to be done rigorously. So I'll not say more about that, but I just wanted to point that out. Okay, so that's what I was trying to say there. So what is the actually result that we have for the time domain, which gives us the uniqueness result for the frequency domain? So I'm going to restate the problem. So I'm not just putting a u sub q just to denote the dependence on q. So this is where the data is in the u sub q. It's a solution of the characteristic initial value problem. Here's the initial data. And this uq, this is the value on the inclined plane. Okay, and this connection is really important. That uq at any point xt on the inclined plane is equal to the integral of q on a line parallel to omega, starting at the point xt. Okay, but of course our data is not on the inclined plane, right? Our data is on the boundary of this cylinder. So we have a map, the forward map F from Q to the value of this UQ on the boundary of this cylinder. And the goal is to, of course, invert and prove the injectivity of this. And so what Mikko and I were able to show was that, so you fix your omega, and suppose you have a Q and there is a perturbation P. And they're both supported inside this unit ball. And you have to, there is time involved here, which I haven't been very explicit in my image. So time has to be big enough in relation to the diameter of the ball. And then, of course, P and Q have to be smooth and bounded above and so on. So then we show that the perturbation, the L2 norm of the perturbation in the interior can be bounded by the H1 norm of the difference in the data on the boundary of the cylinder. There is another term you have to add, which is this E. E is actually this curve of intersection of the plane with the boundary of the cylinder. That term has to be added, but it's also part of data. It just takes a different norm. It's a norm on a, if you like, a curve versus this is norm on a surface. Okay. So we have this estimate. So we have a Lipschitz stability estimate, but of course the data here, there are conditions on it. Firstly, either we have to have data from omega and minus omega on the right-hand side, or we have to assume that a perturbation P is even or odd in the direction omega, say Z, and or we have to assume that the derivatives of P in directions perpendicular to Z are controlled in a certain way. So that is the result, the time domain result, which we proved. And from this, because of the equivalence with the frequency domain, one gets injectivity. And the way we do it is we use the Bukhgeim-Klibanov method, uh, which is a Karl-Liman estimate-based method. And the Bukhgeim-Klibanov method was first done for the uniqueness problems, and it was modified by very important modifications by Yamamoto, Puel, Emanuela, Visakov, Bilasware, and others. And we use this modified method. I'll say more about this method a little bit later. Sorry, what's the time? It's 24, okay. So I will come back to the Bukhgeim-Klibanov method, but now I'd like to talk about the second result that we have. And that's the work which is done with Venki Krishnan and Somin Senapati. And it's for potentials which depend on space and time. And as I said, we just finished it and I've posted the article on arXiv today, so it should be available tomorrow. So let me first describe the space and time dependent problem that has been studied. Our problem is slightly different than what I'm going to first describe. So the problem that is studied often here is a bounded domain problem. You have a bounded domain B, and there is this cylinder, and we have this function Q of xt, which is defined inside the cylinder. And you probe this medium by initial data F and G, and you have boundary per data, so not data, initial source is F and G, and boundary source H. So under appropriate conditions on F, G, and H, this is a well-posed problem. And so you can define a Dirichlet to Neumann type map, I'm going to call it Dirichlet type, which sends the initial data F, G, and the boundary data H to the normal derivative on the boundary, on the lateral boundary, and the value of U and UT on the top. So we need interior measurements, but we need it only on the top. But remember that the coefficient Q depends on time. So even if you can do measurements at the top, doesn't mean we have any information directly in the interior. So L is here the lateral boundary and H is the top. So just, it looks a little messy here, but so we define this Dirichlet Neumann type response operator, which is the response to the initial input F and G, the source is F and G, and the boundary source H. and we map it to the normal derivative on the boundary and the value of the solution u and ut on the top. So the question arises, sorry, of course, yeah. So the goal is to do the inversion of this map. So you have the map from q to the response operator lambda q, and we want to invert it. Uh, so the unknown q of xt depends on x and t. And so the first question which arises is, normally for most of the initial Neumann map problems, one does not use initial data. One just uses boundary data, and the response is also only measured on the boundary. So why are we doing initial data sources, and why are we measuring information on the top? Okay, and this is related to the fact that Q actually depends on time. So if Q is dependent on time, if you did not have initial sources, because of the speed of propagation, you will not be, the value of the medium inside here near the initial t equal to 0 cannot be sensed purely by boundary data. You can actually draw certain cones here, and you can see that there'll be no information about that part of the medium in your boundary if you do not use initial data sources. Okay. Same thing at the top. If you do not measure information on the top, you can draw a backward cone from the top, and there'll be no information about that part of the medium in the boundary data. So that is one of the reasons why one has to use initial data sources and why one has to make measurements at the top. A natural question arises, okay, let's not use initial data sources, don't make measurements on the top. Just recover the Q on the part which can be sensed. And that's a very good question. And as far as I know, no one has been able to do anything with that for that problem. They can do things with that problem, but then they assume we know Q on the remaining part. But just not knowing Q anywhere and recovering Q just from boundary data and boundary sources on the relevant part, as far as I know, no one has done that. There is a way around not using initial data and not measuring at the top, but the price you pay is you have to do measurements for infinite time. So if you do infinite time measurements, then you don't need initial data and you don't need measurement at the top because the issue that I said doesn't arise. Okay, but we are going to stick to this problem here where we have initial data and we're doing finite time measurements. So what are the results that are known? So this map from Q to the lambda Q, the response operator, results that are known are this: injectivity is known. There's actually logarithmic stability for the QXT problem. For if Q was independent of time, there is actually holder stability, but right now it's QXT, this dependent on time. There is, I believe, only logarithmic stability. There are also partial data results, and there are a lot of interesting work here. It started with the work with Stefanov and Shostrand and Ram, and that was in the frequency domain. So I did some work in the time domain. There is Salazar's work, Belisud, Kian. There are many others. I'm sorry if I've omitted someone, listing someone here, but there are many other people. They have worked on this, and there are these results. I do want to point out one thing here, that this is an overdetermined problem. Because the response operator, so if you look at the kernel of the response operator, then you're allowing your initial data, let's say just to initial data. So that's n dimensions. And then you measure, let's say on the top, that's another n dimensions. So that's 2n dimensions. So the data corresponds to 2n dimensions, and you're trying to recover a function of n+1 variables. So that's an overdetermined problem. And the results are obtained by using products of geometric optic solutions. But having said all this, I would like to point out a very recent paper of Lasas et al. There are four authors for that, which deals with, instead of QU, there's QU to the power M. So it's a semilinear problem. And they are able to prove stability and uniqueness um, for that problem. And actually the data is, if you do the data count, it's actually an underdetermined problem. Um, their coefficient depends on n plus 1 variables, and the data is, as far as I can count it, it's depends on n variables. But the fact is that it's semi-linear, so there is u to the power m, and then this creates, using the right input, you can create sort of sources in the interior. At least that's how I understand it. So there has been, I think, a fair amount of work on things like this, where the linear problem has not been solved, but the nonlinear problem or the semi-linear problem has been solved with strong results. So now this is the situation, but we will study a related problem, which is formally determined, and we have Lipschitz stability results. So it'll be formally determined, but still have Lipschitz stability actually. So I want to state what the problem is. So this is work done with Venki Krishnan and Soman Senapati. So Q of xt is now, the first difference is that our problem is on the free space. So this is actually, if you like, a weakness of our method and our problem. That is only for a free space problem. We cannot do this on a bounded domain. We don't know how to do it. So Q of xt is a smooth function on free space. You can, time is not an issue. You can fix time. And it's supported in a bounded domain. And we assume that Q is 0 from some time below. And again, so it's a fixed angle scattering problem. So what we do is we probe this medium with a plane wave. Okay, so notice that at least one weakness is gone. We do not have any interior sources FG. All our sources are coming from the outside. Okay, so we have plane waves. So that's not an issue for us. We don't assume interior sources. We send in a plane wave, and notice there is a parameter tau here. Okay, so we are sending in plane waves, but different delays. Okay, and that is going to be important for us. So there is a different, you send in a plane wave, then you send in a plane wave later, and you send in a plane wave later. And that is going to be important for us. That's because Q depends on space and time. If Q was independent of time, it wouldn't matter, the delay wouldn't matter. So we send in the plane wave. So of course, there'll be the usual, there'll be the principal wave and then the response wave. I'm not going to write it down here. Well, actually I do. So you take the difference between the full and you subtract from it the part which doesn't depend on Q. And so that's the U part that we'll be working with. Okay. And our data is going to be, we measure the value of U on the lateral boundary and we measure it on the top. Okay. So it's like the fixed angle scattering problem. We measure on the lateral boundary, but fixed angle problem, we don't measure on the top. But for this time dependent thing, we do measure on the top. And as explained before, why we need to do that. Okay. So our data consists of lateral boundary measurements and the measurement at the top. Notice we do not have interior sources. Our source comes from the outside. Okay, and the goal is to study this map. And the very important here, there is a parameter tau, and we have data for all tau. So we are allowed to send plane waves at different times. Okay, and but they're all coming from the outside. Okay, and if you notice that this problem is actually formally determined, Q depends on n plus 1 variables, and the data depends on n plus variables. So having this extra parameter tau is important. If we did not have that tau, it would be actually an underdetermined problem. So what we prove, now again, there is the usual hypothesis about boundedness and so on. So what we prove is that if you have Q and Q acute, two potentials with all these properties, then the L2 norm of the difference on this whole cylinder is estimated by the H1 norm on the lateral boundary and the H1 norm on the top. There's another term on that ellipse, which I haven't written, but there is a term on this curve of intersection of the plane and the cylinder. Okay, so we are able to prove lift shift stability for this formally determined space-time problem. And the way we prove it is, again, by using an adapted version of the Bukhgeim-Klibanov method. Um, so that's the result. So let me just tell you a little bit about the Bukhgeim-Klibanov method, and it'll be very brief. And then I'll also tell you, where the two, why do we need two plane waves for the QX? Notice, by the way, here we don't need two plane waves, but that is because we measure two measurements at the top, and that helps us. Actually, this problem, the way I've described, is actually in some ways easier than the problem which I did with Mikosalo. Actually, I also need to add one more thing here. We also have results when you allow first order perturbations here. The magnetic potential case, we also have similar results now. So I'm going to talk about, go back to the fixed angle scattering problem where Q is independent of time. And why do we need two measurements there? And what is this Bukhgeim-Klibanov method? Um, so I'm only going to take two slides, so it cannot be really very detailed. So Bukhgeim, I just want to say something actually more. Those of us, who work in inverse problems, we've seen Karleman estimates used in actually two different ways, two completely different ways in inverse problems. The first one is this Bukhgeim-Klibanov method in 1981 I'll talk about, um, uh, which is perhaps people who work on elliptic problems may not know about this. So, but in the elliptic problems and to some extent for hyperbolic problems, Kalaman estimates have been used to do the Dirichlet-Neumann type problems for partial data problems by constructing special exponentially growing solutions. Okay, and that was a very clever use of Kalaman estimates. It was, I'm not, I may be wrong, but I think it was started by Keeney, Goldman, and Chostrand and Salo. So they used that in a very clever way to construct special solutions for elliptic problems for partial data problems. And that use of Karleman estimates has sort of quite widespread for elliptic problems and also has become widespread for hyperbolic problems. I think that was done in the 2000, but there is this other use of Karleman estimates, which was initiated by Bukhgeim and Klibanov to actually obtain stability results for hyperbolic problems. For a single solution. And that was done in 1981. They actually proved a uniqueness result for these formally determined problems. It was very important modifications by Isakov, Imanuvilov, and Yamamoto, and a few others which I haven't listed here. And they made a very important adaptation so that it could work for stability problems. And we used those adaptations. So let me describe what is the Bukhgeim-Klibanov problem, or it's the modified Bukhgeim-Klibanov problem. Okay, this is on a bounded domain. B is the bounded domain. So this is the cylinder, B cross 0T. S is the boundary. And so whenever we do inverse problems, coefficient determination problems, we take two solutions, we take the difference. And then the difference of the two solutions shows up on the right-hand side as a px. That's what this px is. It's the difference of, difference of the two coefficients, and gets multiplied by one of the solutions. That's typically how we do these inverse problems. We take the two solutions, take the difference of the coefficient shows up as a px and gets multiplied by one of the solutions. Okay, so one might as well just study these inverse source problems. Okay, and this is what Bukhgeim and Klibanov did. So they do an initial boundary value problem. There is a source p of x and some arbitrary function vxt. Okay, except they have this thing here where the initial data also has that unknown px. Okay, I'll talk about this in a minute. And ut is 0. And you can, when you have the normal boundary, you can take the difference, it becomes 0. So the modified Bukhgeim-Klibanov problem is actually, you have given this px, determine the, given the map from P to the boundary data, this is just lateral boundary. Given the value of the solution on the lateral boundary, can we recover the coefficient P? Okay, that's the Bukhgeim-Klibanov problem. This is a formally determined problem. And this is what roughly Bukhgeim and Klibanov wanted to study. Okay. So the first question which people always wonder, I mean, how come your unknown coefficient is showing up in the initial data? I mean, that's unfair. Okay. So, but first, let me say two things. Firstly, even if the initial data is here, this is still a very difficult problem. It's a formally determined problem, and it's very difficult still. And I'll explain what's the issue. And secondly, how did this initial data show up here? So actually what Bukhgeim and Klibanov did was that they had used an internal source, which was positive throughout the medium. So that's actually artificial, but that's the best that could be done at that time. They used an initial source which was positive in the interior everywhere. And because of that, with some modification, that's how this P of X shows up. Okay, so then the question is, what about our fixed angle scattering problem? How does our P of X show up in the interior? Okay, and this is where I was pointing out to you in the beginning. That is very important. Let me go back and just point out again how the PX shows up in the interior. Okay, just it'll take 1 second. And that is a very important point. Yeah, so remember this, well, actually, let me go back 1 step further here. So this was the problem we were working on. We send in a plane wave. So all the sources are outside. There is no interior source here. Okay, so our source is outside and it's a plane wave. But then you look at the response, then the response is actually a solution on the upper half plane. And the U value of U on the half plane is directly related to the coefficient. Okay, so this is that thing which, how come we get the P in the interior? That's how it shows up for the fixed angle scattering problem. Okay, but remember that we do not have measurements in the interior. So just the fact that there is a relation doesn't really mean it makes the problem simpler. All our measurements are on the boundary, but the relation between U and Q is in the interior here, and there is an explicit relation. And this is important. So let me go back. Yeah. So now I've sort of tried to explain to you how this P of X shows up, at least for the fixed angle scattering problem. Of course, notice for the fixed angle scattering problem, we don't have data at T, the connection is not at T equal to 0, but on the inclined plane. And I'll tell you the modifications that are needed for that. So the question that Bukhgeim and Klibanov and the adaptation they wanted to study was this problem: how do we recover P of X? Okay. Now you always say, well, it's P as the initial data. So you actually, let's say you do standard, so what is called boundary controllability estimate. Okay. Oh, sorry. Okay, I'm going to say that in the next slide. So typically such problems, one of the techniques which has been used is, you take this PXVXT. This is one solution, you multiply it by another solution, study the integral related to data. And that's how a lot of these problems have been studied. But they require using many V's and many solution W's here. Of course, in these problems, there is no PX in the initial data. Okay, so that's how the overdetermined problems were studied. We are going to study it. So we'll have a fixed V. We don't have many solutions. There's only one solution. Okay, and if you do the, boundary control estimate, then you can, loosely speaking, estimate the initial data with the boundary data. That's our data. But then you have a right-hand side that also shows up. So you can see that it's not so trivial. Even if the P is there here, we don't really quite know how to manage this P of X, which shows up on the right-hand side. It shows up here. And this is what the problem is. No one sort of, until the Bukhgeim-Klibanov argument, no one quite knew how to handle this for a single solution. And this is useful only if V is small or time is small. Then of course this right-hand side P of X can be absorbed in the left-hand side. But otherwise, so you can see that even having Px in the initial thing, you still face the same issue which all we face in all inverse problems. How do you manage the Px on the right-hand side? And this was the idea of Bukhgeim-Klibanov, and the adaptation is actually to use weighted estimates. So you use weighted estimates for the initial data. So there'll be a weighted Px norm, and there'll be a weighted Px Vxt norm. Okay. So the Karleman weights, there is a large parameter sigma, and this was important here. You have to choose the weight phi, which is strictly decreasing with time. So the maximum weight is at t equal to 0, and that the weights in the interior for higher t are actually less. And then there is a sigma large parameter. So you have to use a Karleman weight, and you have to use such a weight. Okay. Then you can get a similar such estimate. It's not so trivial. There are some issues which I will talk about in a second. Then you use the Karleman weight, and the fact that the weight on the b cross 0t, the phi of xt, is smaller compared to phi at x0, allows you to absorb the right-hand side p of x in the left-hand side. Okay, so that's the trick here. The question is that how do you get this weighted Karleman estimate? Okay, if you do a Karleman estimate on this cylinder, then actually the contribution from the boundary at t equal to 0, part of it has the wrong sign. So actually you don't get this ux0. This doesn't come out from the Karleman estimate if you do it on b cross 0t. The t equal to 0 boundary term has part of the derivatives have the wrong sign. So what Bukhgeim-Klibanov had to do was, and they used this condition utx equal to 0 to do an even extension of this into the cylinder minus t to t. Okay, that condition is used in doing minus t to t. And then because the weight at capital T and minus t is very small, you can use Karleman estimates, and you get an interior estimate in the domain, and then combine it with a weighted energy estimate. This was the modification actually made by Ivanovich and Yamamoto and others. So this doing a weighted estimate and then combining it with weighted energy estimates, and then you can get an estimate like this. Okay, so there are some complications involved. And then you can use this trick about the weight is small at the largest at t equal to 0 and small at other t's. Okay, so then the question is, why do we need the two directions for the fixed angle scattering problem? So where is that used? So remember how we use the ut equal to x equal to 0 to extend it to minus t to t. We did not want to deal with t equal to 0 in the Karleman estimate. We only want to deal with t and minus t and t. So how do we do that for the fixed angle scattering problem? And let me see if I have that picture back here. So for the fixed angle scattering problem, our solution U is on one side of this half plane. And if we try to do Karleman estimates on one side of this, we'll get boundary contributions from this, which we want, but some of the terms will have the wrong sign. So we have to do an extension to the full cylinder so that we don't have to deal with it first. And the weight on minus t and t is small. So we want to do it for the full cylinder, but how do we extend the solution? And this is where the second solution comes into play. If you have a solution coming from the opposite direction, the wave coming from the opposite direction gives us another solution, which we flip around and put it underneath this plane wave. Okay, of course, you can put any solution underneath this plane wave, but the important observation is that the jump in the U from the top part and the bottom part, because they're from two opposite directions, the jump in the U is actually related to the data that we measure on the boundary. So that is the crucial thing here, and that allows us to add the second solution underneath and work on the cylinder, and then try to imitate the Bukhgeim-Klibanov argument. So that's where we need the second solution, is to put it underneath the plane wave, and so that we can do an extension, and then the jump across the U in this is related to the data. If you don't want to use a second solution, which I said some results, if you just want to work with one solution, then you have to control the negative terms which come from this. You have to control those derivatives, and that's where the control on the coefficient condition comes if you want to use only one incoming wave. So that's all I have to say, and thank you very much.
I'm sorry. Thank you very much, Rakesh, for the very nice talk. Thank you very much. Are there any questions or comments? Please. Okay, are there any questions or comments?
Okay, I have a question.
Please.
Sorry, who's that?
Jillian from Michigan State.
Oh, okay, I see. Okay.
Okay, so do you have any numerical results to justify your theoretical theorems?
I see. Okay. Yeah, actually, I wish I had. There is. So the Bukhgeim-Klibanov result is very old, and then the work by Yamamoto and stuff. It was all done in. I think it was all done by 2010. Now there is a French group. I wish I know one. I've even met one of them. They have actually done a numerical algorithm for the Bukhgeim-Klibanov problem. Okay, where there's I don't know anyone has tried to do anything for our work with Mikko, but I know that they proposed an algorithm, and I think they've implemented it. There's a group in France. His name is slipping from my mind, but they have implemented, I think, the Bukhgeim-Klibanov problem.
Another question. For wave equation, usually even dimension, odd dimension, the solution will behave differently. So in this setting, in your setting, do you have a difficulty difference in treating different situations?
No. So plane waves, I think the behavior, it doesn't matter. If I was using point sources, that might make a difference. Right? The fundamental solution actually for the odd and even cases, there's a slight difference in the behavior. Of course, you're working with perturbations of that, so I'm not sure any effect is left. But if there is anything, if you use point sources, you might notice the difference, though I'm not sure.
Okay. Okay. Thank you.
Okay.
Thank you very much. Are there any other questions or comments?
Hi, Rakesh. This is Shiki.
Oh, hi. How are you?
I would like to ask a question. So, this kind of method, can it completely solve the inverse medium problem?
Okay, so
because there involves some reflection. Yeah.
Like you mean that because we're using two direction, is that what you mean?
Yes, I mean this could we further reduce the data set to just one.
If I knew it, I would have done it.
Okay.
Sorry, I don't know how to make it work. I don't. So I don't know if Mikko has any ideas. But as I said, if I knew it, I would have done it. I mean, it's. I don't know if I can do it. So as I said, I've been working on inverse problems since my PhD. So 1982 and stuff. I've had two problems in my heart from then, 1982, the fixed angle scattering problem and the backscattering problem. So I've made progress, and I'm going to sort of try to work on the backscattering. I've been trying to work on it for a long time. So anyway, that's been my dream for a long time. So.
Thank you very much.
Sure.
Thank you very much. Are there any other questions or comments? Please, are there any other questions or comments? Okay, if not, thank you very much, Rakesh, for the very interesting talk. Thank you very much. Thank you very much, everyone, for coming. Thank you very much.
Okay, bye.